Okay, now we're going to talk about another constant acceleration problem. This one is going to deal not with vertical motion, which has a constant always acceleration of negative 9.8 meters per second squared, but we're going to be dealing with sideways motion, in which you can have a little bit more customization. A ball is traveling with constant velocity east at 3 meters per second, so it's going this way. East is to the right, usually. When it hits a spring that slows it down with a uniform acceleration of 4 meters per second squared. Springs are usually drawn in physics diagrams as these little swirly things. So swirly, and then we'll say that that's like attached to some sort of block. In the direction opposed to the ball's original motion. Well, obviously, the ball is not going to get sped up by the spring initially. When it hits the spring, it will compress the spring and then it'll slow it down, and then it will get sped up as it gets launched back in the opposite direction. So the acceleration that the spring imparts to the ball is to the west. When the ball stops, the spring then accelerates the ball again with the same magnitude and direction of acceleration. The acceleration of the ball after it stops lasts the same amount of time as its initial slowdown. So as long the amount of time in which the ball is compressing the spring and being, this isn't really a physics type word, but decelerated or accelerated in the westward direction, it is also being sped up or recelerated. I don't know if that's a word at all, but sped back up so that it now is traveling west. The spring acts on the ball for the same amount of time in speeding it up as it did in slowing it down. How long does it take for the ball to lose all its initial eastward velocity? If you think about it, this really will use one of the equations that we already saw in the prior problem, because we can solve this one by saying velocity final equals velocity initial plus acceleration times time. Lose all its initial eastward velocity means that the final velocity must be 0. So final velocity is 0. Initial velocity we knew was 3 meters per second. And now here, this is where you have to pay attention to details. The uniform acceleration of 4 meters per second squared is opposed to the ball's original motion. A is not positive 4, it's negative 4, okay? And then this is times the time, which is unknown. It also happens to be what we're looking for. We can solve this. Move the 3 to the other side, and we get negative 4t equals negative 3. Divide by negative 4, and t will be equal to negative 3 over negative 4. The minus signs cancel out. That's 0.75 seconds. So that's the answer to number 1. How far does the ball travel during the time it is slowing down? This is the amount the ball compresses the spring. This also can be solved using the same equation that we did before. I'm wondering if we can use a different one, though, because it would be nice to see how another equation works. Let's see about using, maybe we can use this one. Instead of x minus x naught, I'm going to just write delta x, the change in x, and then I'm also going to simplify the subscripts a little bit. That equation says that the final velocity equals the initial velocity, both are squared, plus 2 times a times delta x. I want to examine whether we know these things or not. Do we know the final velocity? Well, how far does the ball travel during the time it is slowing down? At the end of it slowing down, it will have 0. So yes, we do know this. That's 0. The initial velocity is known as well. The acceleration is also known. So the only thing we don't know here is delta x. But in algebra, not knowing one thing is good. So let's swap in the values that we do know. Vf, if we're talking about the slowing down process, is 0. V naught is known to have been 3 meters per second. That's right from the problem, east at 3 meters per second. And now 2a delta x, 2 times negative 4 times delta x. Again, it's good algebra because there's only one thing we don't know. This means let's see, we'll move the 3 to the other side and multiply through the parentheses. This becomes -8 delta x equals -3. Negatives cancel, and delta x will be equal to 3 over 8. 3 over 8 is 0.375 meters. So how far does the ball travel? It's 0.375 meters. Sometimes when you're talking about spring compression problems, especially later in the year, you might refer to this in centimeters because that's a typical unit to refer to spring compression. So you would call this 37.5 centimeters. Now, this next one is, it's a little different. Hang on, I'm going to get an extra page in here. This next one is a little bit different because now we're asked to do something conceptual, not so much calculation-based. Provide an argument based on symmetry that the ball will have the same westward speed at the end of the ball's interaction with the spring as it had eastward speed at the beginning of its interaction with the spring. So this is saying that the ball gets launched off with the same westward velocity as it initially had eastward velocity. But I want you to think about this. The ball gets slowed down with a certain acceleration, right? It then is acted on with the same acceleration for the same time. So the acceleration depletes the initial velocity. In 0.75 seconds. It then continues, yeah, I can spell, continues to act for another 0.75 seconds. Now think about it. If the initial 0.75 seconds is enough to bring the ball to rest, then continuing to act for the same amount of time in the same direction should launch the ball with the same exact velocity, but in the opposite direction. So since V naught went to 0 during the initial, the launch should be enough for 0 going to V naught again. Except now we are going in the opposite direction, so we need to label it as minus. We're making good progress here. 1, 2, 3. Now draw a velocity time graph for the ball's motion. For the ball's motion, we'll have some sort of like initial time that it's traveling with constant velocity. It will then hit the spring, and then it will get slowed down, launched back in the opposite direction. Okay. So let's say we'll keep it conceptual for this, like not too terribly much detail, except we might need to, I don't know. Let's agree that the eastward direction is positive velocity. So the initial is, I believe we said it was 2 meters per second. We just provided a good argument that it's going to have -2 by the end of this. I want to depict it going at a constant 2 initially, just so that it's not a downward slope, like purely the whole time, but then it hits the spring. And then it uniformly accelerates in the negative direction until it is released by the spring and continues with uniform velocity again in the westward direction. In order to make this fairly detailed, I do want to label it with like a length of time. So from here to here, this would be a length of 0.75 seconds. I don't really care how long the initial uniform velocity is. I don't care how long the afterward eventual velocity is either. I don't really care about that. What I care about is the length of time that the ball is interacting with the spring. What is the last thing? see if you can draw a rough position time graph as well. I'll say well, we'll make a judgment call as to whether we want to do it just during the time that it's bouncing off the spring or not. We should be able to see that this is actually harder. Why? If it is, well, we'll give ourselves room in both the positive and negative direction. Something that your class may have gone over yet or will go over soon is that when the velocity time graph is flat, that means that the position time graph will be tilted. If the velocity is positive, it will be a positive slope for the position time graph. If the velocity is negative, then the position time graph will have a negative slope. But if the velocity time graph is sloped, then the position time graph, like, see how flat turns into sloped? Well, where does sloped have to go if it's already sloped? It turns into a parabola. It gets kicked up by 1 degree of polynomial. So purely constant turns into a linear polynomial. A linear polynomial turns into a parabolic or quadratic polynomial. So this is going to be traveling in the eastward direction. It should look something like this. It will have, I'll get a different color. It will go something like that, where this is the time that it's interacting with the spring. So it's a little bit more difficult because we don't know where it started. We don't know how wide the parabola is, etc. So these are a little bit more difficult to draw. If you are taking calculus at the same time as physics, or maybe you're taking a physics-based calculus class, you will be familiar with the fact that velocity is the derivative of position and acceleration is the derivative of velocity. On the other hand, if you want to get the position, you find the integral of the velocity. If you want to find the velocity, you find the integral of the acceleration. The integral of a constant function is a linear function. The integral of a linear function is a quadratic function. So these things are easily related, but if you don't know that, it's still okay, because think about the fact that velocity is changing. If velocity is changing, then position should not be changing smoothly. It should be changing in a sort of curved or accelerated sort of way. That's the idea here, and that's what makes it a little bit harder to draw.